University is going to talk about magnetism of the 166 kagome metals.
Okay, got it. So, right, so I'm Rob McQueeney. I'm from Iowa State University and Ames National Lab, and just going to say I'm quite comforted to see so many people here who have come through Ames at some point in the past. So I feel quite welcome here, and especially the connection between Ames and Brazilian scientists seems to be quite strong. I think that will continue to be strong. So in this talk, I'm going to talk about these rare earth transition metal 6x6 kagome metals, and I think Eduardo maybe mentioned kagome metals a little bit in his talk, but I'll spend a little bit of time sort of giving you an outline of kagome metals and why they're interesting. So just a brief outline of the talk. So the kagome metals are interesting because you can get these uncommon band features like Van Hove singularities, flat bands, Dirac cones. And if you can position these close to the Fermi energy, those can be a recipe for getting very novel quantum and topological phases. In these rare earth transition metal 6Sn6 kagome metals, you have bilayers of these transition metal-based kagome layers separated by a rare earth layer. And so one thing that's interesting to think about is whether when you have magnetism on these rare earth layers, whether those can influence the quantum phases or the responses that you get from these kagome electrons. And so these magnetic phases, they're actually quite complicated. They can be sort of complex and rich. And so my talk, I'm principally going to be describing the magnetism of these materials. So I'm an experimentalist, neutron scatterer. And so we use neutron and X-ray scattering to get a good idea of a magnetic model for these materials. These models are predictive. They allow us to calculate phase diagrams and predict all these complex collinear, non-collinear, non-coplanar magnetic phases. These models are good enough that we can get the magnon polarization vectors out, and we can answer questions about things like the development of scalar spin chirality in the systems due to magnon fluctuations, which is a theory that's out there now. And of course, the most exciting thing in neutrons is when the model fails, because usually that implies that something else is going on that's interesting. And so I'll give a couple of examples where these models fail that perhaps give us some insight into these sort of novel kagome electronic states. So, of course, this is a big collaboration. So at Ames Laboratory, we have quite a bit of a cross-section of experiments and theory there. A lot of the work here is catalyzed by at Ames-led what's called an Energy Frontier Research Center. This is one that I direct called CATS. It's a multi-institutional center. So we have quite a lot of interest in these materials running through CATS. Thais was a postdoc there, and so she continues to work on some of these. And we do neutron scattering in Oak Ridge, and we have a variety of other collaborators around the world. So just a very brief outline. I'll introduce a little bit more detail these 166 kagome metals. I'll talk about a couple of examples that are quite interesting. One is Ising ferromagnetism in the rare earth vanadium 6Sn6. Here we can talk about things like whether transverse field quantum criticality might exist, whether those fluctuations may couple to kagome electrons, and then we have some evidence for some maybe exotic time reversal symmetry breaking. And then we'll talk a little bit about complex magnetism in the rare earth manganese 6Sn6 compounds, especially focused on how chirality might develop, magnetic chirality or spin chirality might develop in these systems. So yeah, so here's going back a step and introducing these kagome metals a little bit. So of course, the operative thing in the kagome metal is you have this corner shared triangular lattice. If these were insulators, this would sort of be a platform for things like spin liquids due to the frustration of these corner sharing network. If you have a metal, you can get, again, this dispersion here where you have these different kind of features. If you have flat bands, or if you can tune EF near a flat band or Van Hove singularity, you can, of course, get many correlation-driven phenomena, itinerant magnetism, charge density waves, superconductivity, and so on. Things like flat bands, they have their own sort of interesting peculiarities. They would have a churn number if they can kind of separate them off from this band here. And also because of this frustration, there's destructive interference of the electron hopping, and so in this flat band, for example, the electrons are localized to these hexagonal plaquettes here. Also, if you can get Dirac cones close to EF and you can magnetize the system, it's a recipe for things like Weil semimetals or churn insulator. So, over the last few years, there's been quite a bit of interest in these materials. There's certainly several families of these materials. You have these, of course, they're all layered because you're interested in these two-dimensional layers. You have these intermetallics with transition metal kagome layers and some other atoms here in different ratios. In that larger family, you go from sort of 3 to 2-dimensional systems. You have correlated metals, which are sort of on the verge of maybe magnetic order, itinerant ferromagnets, charge density wave systems that coexist with magnetism, Weil semimetals. You also have these other cobalt-3, tin-2, sulfur-2, which are very high anomalous Hall effect Weil semimetals, which is sort of a signature of the large Berry curvature. We heard a little bit about these AV3SP5. These are very interesting charge density wave systems, which are also superconductors. There's some evidence for maybe some unusual time reversal symmetry breaking. There's no demonstrably magnetic atom in that crystal. And then we come to the rare earth transition metal 6-tin-6. Again, these are bilayers of kagome, which are separated by a rare earth triangular layer. And the focus on these is the various magnetic states that you can get. So, going back a few years, these materials have been studied for a while, actually. So maybe starting at about 1990, and the interest was that they sort of followed the formula for developing a hard permanent magnet. So if you have a hard permanent magnet, usually you want a high TC and a large anisotropy. And so you'd want a magnet that had strong transition metal ferromagnetic exchange, and you'd want to couple that with a rare earth that has a strong anisotropy, and you want those to be coupled, and that coupling is usually antiferromagnetic between the two magnetic sublattices. So materials like neodymium iron boron, samarium cobalt-5 would follow that formula. So with the rare earth manganese 6-tin-6, you do have these sort of ingredients for nice magnets. And so early on, these were discovered to have very large TC. So the manganese, in this case manganese, and the rare earth order simultaneously well above room temperature. And so it was known then that they do adopt a variety of magnetic structures, and then single crystals were developed at the Ames lab. I think Paul Canfield was part of that development sort of in the late 1990s. And where they, with these single crystals, they were able to discover lots of metamagnetism and tunability with field and chemical substitutions and so on. And so, go ahead 20 years and, these kagome metals come back into vogue because of the electronic properties. And so you can look at different transition metals. All of them have these different operative features close to the Fermi surface in principle. So if you look at yttrium chromium 6 germanium 6, it looks like a pretty nice example of a kagome flat band material. If you look at the vanadium, it has both saddle points or Van Hove singularities and Dirac points, which are close to the Fermi surface. It would seem in this case that the Dirac cones are somewhat operative. And then in yttrium manganese 6-tin-6, you also have Dirac cones and flat bands, which are operative. The issue here is that you have, in these transition metals, 5d orbitals, and so you can get Dirac cones and flat bands both near EF in certain cases. So this sets sort of the context for looking at different kind of novel effects of the magnetism of the rare earth on these materials. So, I think that really interest in these kicked off, for better or worse, with some prediction that you could have a churn insulator in these rare earth manganese 6-tin-6 where the moments were pointing perpendicular to the kagome layer. And you can get that by coupling to terbium, which is a strong uniaxial rare earth. You also go to the other end of the spectrum here with ytterbium and vanadium, where the vanadium is non-magnetic, but this ytterbium sort of nucleates a nice heavy fermion phase. If you apply a magnetic field in terbium vanadium 6-tin-6, there's evidence that you can develop a giant orbital magnetization due to Berry curvature. And also, if you apply a magnetic field in some of these rare earth manganese 6-tin-6 compounds, you see evidence for topological Hall effect, which might tell you that there's a scalar spin chirality which develops in these systems. So it's actually these last two that I'll focus some time on. So the objectives here then are really to understand what the magnetic interactions are, what the anisotropies are that lead to these magnetic phases, and then to understand how the spin dynamics can control these magnetic phases, things like rare earth spin fluctuations, or how the spin dynamics can drive the development of scalar spin chirality. And like I said, when these models fail, it's interesting, and it might provide a window into studying how itinerant magnetism develops in these kagome layers. So I have a couple examples of that. So what do we do in our experimental program? We have single crystal growth. I think somebody mentioned they're small crystals, but if you have a lot of them, you can do neutron scattering. Can't remember who said that. It's true. These are small crystals. We have a lot of them. We co-align them to do neutrons. So we do have a lot of crystal growth here, and magnetic characterization, inelastic neutron scattering done principally at Oak Ridge. That allows us to develop magnetic models and look at other collective excitations. We have all this data. We have various modes to analyze it, linear spin wave theory and sort of mean field analysis, or we can, if we're looking at crystal field excitations, we can use an RPA approximation, so there's some nice comparisons here, or density functional theory. So this is sort of work of a PhD student, Tan-Chong Han, and this has to do with one of these materials, terbium vanadium 6tin6. So this isn't our work here, but rare earth vanadium 6tin6, the operating story is that the vanadium is non-magnetic. And so the rare earths are magnetic. And so they'll order at low temperatures below about 5 Kelvin. You get these so this shows the different magnetic structures as a function of the rare earth. They all have ferromagnetic planes, and they have different anisotropies, and that anisotropy just comes from the nature of the rare earths. And sometimes they're completely ferromagnetic, but in some cases they're antiferromagnetic. The layers are antiferromagnetically coupled. So there's one oddball member of this series where you put in scandium, which is non-magnetic, and this will give you a charge density wave ground state, 90 Kelvin. I'll come back to this a little bit later, but the short story is there's no magnetism in the kagome layer, but you do have magnetism in the rare earths, and only the scandium will show this charge density wave. It's not seen in these other magnetic rare earths. And similar to the 135 kagome metals, there's some evidence that maybe time reversal symmetry broken in that charge density wave state. Although otherwise, I think the charge densities aren't related. We look at terbium. So this is a very strong Ising ferromagnet. So you can look at the magnetization here, which shows a very strong magnetic anisotropy. If you warm up above Tc, which is about 4 Kelvin, you recover R log 2, which tells you you have a doublet ground state, crystal field ground state. If you look at magnetic transport, you can see that there's a strong influence, either in the Hall or just the linear resistivity in magnetic order, so it will influence the conduction electrons principally in the kagome layer. I mentioned this already, but there's evidence for very strong Berry curvature, which you can kick in these Dirac cones near the Fermi surface by applying a very small magnetic field, just a couple of Tesla. So our interest in this material is it's a nice Ising system. We do neutrons. We can look at things like whether it's quantum critical in a transverse field. And we can wonder whether and how these terbium moments might couple to these Dirac cones to give us some novel feature. So I won't go through this in too much detail, but we did neutron scattering here. So these are powder samples. You have excitations, energy transfer as a function of Q. These are two different energy ranges. And what you're seeing here are these dispersionless modes, which are crystal field excitations on the terbium. And so you can kind of sum these all up over Q, and you get these nice spectra as a function of temperature. And so you can fit it to a crystal field Hamiltonian. Given the symmetry of this compound, there's 4 independent crystal field parameters, which we can easily fit with the data. And so we get a spectrum here, which shows, so terbium has J equals 6. So we have a plus minus 6 ground state, which is well separated from all the other excited crystal field states. This is sort of the formula for a nice Ising system, uniaxial Ising system. This state, this doublet, is either up or down. And to get to these other, so if this orders at 4 Kelvin, the gap to the next excited state is 80 Kelvin. So it plays no role in the magnetic order and so forth. No. So this is a long story, which I probably won't get into, but this is one of the crystal field parameters. Yeah, so the crystal field parameter, this is the crystal field parameter that sets the planar magnetic anisotropy. Yeah, so these are based on the fits. Yeah. Right. So the first thing we look at is whether or not there's quantum criticality in a transverse field. So, you know, in an Ising ferromagnet, you might have a ferromagnetic to quantum paramagnetic transition. And in a spin-a-half system, that would come from the fact that the transverse field will mix up and down, right? But in a high-spin magnet, that's not really the mode that works. But we can check, right? So we ran these magnetization measurements at Los Alamos, and we do, in fact, see a transition, spin orientation, reorientation transition, where the moment goes from in the plane, or out of the plane to in the plane. And so with our crystal field parameters, we can understand that this sort of quantum phase transition, it's not critical, it's close to first order, is really driven by a breakdown of this Ising doublet. So you have these other crystal field levels which at zero field are gapped out, but when I apply the transverse field, for example, this blue crystal field becomes stable in the transverse field, and then it crosses, and so I get a metamagnetic transition here, first order transition. The interesting thing is that it would seem like this is strongly first order and it's not Ising at these fields, but you can actually, you're proximate to certain quantum critical transitions in this field range, but it doesn't follow an Ising model, it follows more like a Bloom-Capell model, which is more appropriate for a triplet. So that's something I'm not going to talk about anymore, but we're still working on that with Rebecca Flint. So one thing that's interesting about it, and I said, you know, sometimes these models fail. Well, this is an example where it fails. So if we go deep in the ferromagnetic state of this Ising magnet, then the doublet should be split by the molecular field. And so I should have a characteristic excitation, which is a spin flip excitation from up to down. And so if I'm deep in the ferromagnetic state, flipping that spin, all the neighbors will remain up, and I'll flip this one from up to down. If I have some exchange coupling J, it will cost me an energy of 12Js squared. And so we can estimate J basically from TC, and it would predict that we would have a spin flip excitation of order 1.3 millivolts. So if we can measure this, we're basically measuring J. Okay. But what we find instead is that there's actually two different peaks at this spin flip energy. So the big question is, and they're completely dispersionless, right? So why are there two excitations? In fact, this should be the simplest quantum system you could study. There's only two levels. There can only be one excitation between the two levels. So how do we get two peaks? So, you know, we get a little bit more information from the temperature dependence. So here we see these two peaks, E1 and E2. As we warm up, these peaks weaken, and you can see the fitting of E1 and E2 here, and the gap between them shrinks, but then it remains constant above TC, right? And if I average these two energies, I get a sort of a temperature-independent energy, which actually we associate with the spin flip energy. It's a little bigger than estimated from TC. But if we look at the splitting between these two, it follows an order parameter-like dependence. And so we did a lot of scratching our heads about this, and the conclusion we come up with is that there must be some symmetry breaking that leads to two inequivalent terbium sites. And so in the absence of this symmetry breaking, of course, there's no difference between E1 and E2. They would have the same energy, and they'd be split by this spin flip energy. But there is some symmetry breaking field delta, which increases the gap of, say, terbium-2 and decreases the gap of terbium-1. And so that's much smaller than this Ising field. It's about 10 times smaller. So there's a couple of things, a couple of ways that you can sort of lower the symmetry, right? One is crystallographic symmetry breaking. And since terbium is a non-Kramer's ion, you can have doublets. The doublet can split different, it can split in the crystal field, okay? And we know that there's charge density wave in the scandium, so it could be there's some sort of small distortion and so on. So we spent a lot of time using DFT and point charge models to calculate the effect of different distortions on the crystal fields, this doublet splitting, and it's always very small, much order of magnitude too small. So it's not likely that crystallographic symmetry breaking would explain it. One thing that's much more compelling is that there's actually time reversal symmetry breaking. And the picture for that is pretty simple, right? So and I'm talking about time reversal symmetry breaking that's distinct from the terbium itself, right? It'd have to be some other species, likely the vanadium, that could develop some sort of orbital moment or itinerant moment. It would have to be small. We don't see it with neutron diffraction. But anyway, you could easily see that if you have your terbium here, right, it's flipping its spin relative to the other terbium, but also to some vanadium moment. And so in E1, right, the vanadium would be anti-parallel to the terbium, but in E2 it would be, or to the vanadium, but in E2 it would be parallel to the vanadium. And so there I would get two different splittings, right? And so this is an open question. I'm willing to listen to anybody who has other theories about it, but it seems interesting that maybe we're using this neutron, the splitting of these two peaks, to detect some very sort of weak symmetry breaking in this material. So now I'm going to move on to rare earth manganese 6 tin 6 compounds. I have a lot to cover. There's no way I'm going to get through it, but I'm the last talk, right? So yeah. So this was work done by a postdoc who's moved on now, Simon Ribrols. So with the rare earth manganese 6 tin 6, I explained to you that there's very complicated magnetism. You have two magnetic sublattices, the manganese and the rare earth. The manganese sublattice is strongly ferromagnetic. And the rare earth and the manganese couple antiferromagnetically, just like some of these hard magnets. And so the rare earth magnetic so then basically what I get is a ferrimagnet. And the rare earth magnetic anisotropy can control what type of ferrimagnet is, if it's planar, if it's uniaxial like terbium, or in dysprosium and holmium, it's tilted off the C-axis. If this rare earth magnetic coupling is weak, or it's absent in the case of yttrium, then what forms is a helical magnetic structure. And so this helical magnetic structure come about from having sort of a number of long-range interlayer magnetic interactions which are competing. And finally, you can get, as a function of temperature, various spin reorientation transitions. These always become planar at high temperatures because the manganese has a planar anisotropy. And in a magnetic field, we can get sort of first-order magnetization processes which tell us that there are sort of many different anisotropic states which are close in energy, so they can be tuned easily by a field. You could even get interesting metamagnetic transitions between helical and collinear phases, in this case in thulium. So with neutrons, right, we can measure all these spin wave excitations, right? It's a bilayer system, so we get even and odd out of phase spin waves between the bilayers, and then you could also see excitations coming from the rare earth layer. We can measure all these and fit the data. These pink lines are fit to some, I think it's 10 parameters in the Hamiltonian. So they confirm everything I just said, right? You have some rare earth anisotropy that's specific to the rare earth. You have an easy plane manganese anisotropy. The bilayer coupling is strong between nearest neighbor layers, but you have longer range ones which are frustrated. And so we can take that model for terbium and we can sort of scale the crystal field parameters and we can calculate these nice phase diagrams. In this case for erbium, which would predict, for example, a ferrimagnetic to spiral phase transition with temperature, which we observe, and various first order processes that take us from planar ferrimagnets or spirals into these ferrimagnetic phases or canted phases. And all of these have been confirmed with high field magnetization. So one thing is that, so we talk about electron dispersions in a kagome having flat bands and Dirac points. They're also there in the magnon dispersion, right? It's the same lattice. And so we can look for these sort of topological magnons as well. And so we know the parameters, and so we know where these flat bands, Magnon flat bands should exist. They're pretty high in energy, or these Dirac crossings should exist. And so when we look at the experiment, right, we see these kind of nice acoustic modes here, these odd and even modes here. But when we look for these higher energy excitations, all we see are very overdamped excitations. And I actually highlight a couple here. So in the white box, you see this sort of long vertical streak, which is at the zone center, right? It's a very unusual excitation, looks like an itinerant excitation. And in the yellow box here, you see evidence for other excitations which are higher in energy, which are also smeared out. You see them in different cuts in reciprocal space here. So to get a better understanding of sort of where these modes come from, and they don't come from, well, one of them I would claim comes from linear spin wave theory, the other one doesn't, is we look at the Q dependence. So here we're just taking slices at different energies through these Magnon dispersions. And so when we get to an energy corresponding to the white box here, right, we can kind of isolate it at this energy. You see that we can look at the Q dependence of this excitation. It has an unusual, well, it has a form factor, right, where it peaks up in what I call these gamma prime zones. And then if I look at the higher energy excitation, when the yellow box is way up here, I can see that it has a structure factor which is peaked at the K points at the corners of these zones. So what does that tell us? Well, the structure factor will tell us a little bit about sort of the spin correlations in that excitation. And so the first thing we thought about was, well, if you have a flat band, like we talked about, you have these sort of localized Wannier states where the phase will alternate around the hexagon. You could certainly have that in a flat band Magnon, and if you had that phase wrapping around the hexagon, you would get intensities peaked at the K points. So in fact, what we're observing is the flat band Magnon. It's just heavily damped. But this other one, right, where these intensities are in the middle of these gamma points here, is kind of an interesting one, because it immediately thought of these Q equals 0 chiral antiferromagnets, right? So these are these kind of chiral magnetic structures where you get Bragg peaks in these, what they call gamma prime zones, which are the white zones here. And so we only see intensity in those zones, so you immediately think that it's some sort of chiral magnon, which I would argue is true. So this calculation here sort of matches the data exactly. So we've discovered some chiral magnon. It's not predicted by the linear spin wave theory. We don't know where it comes from. But we do know that, you know, we can change the direction of the manganese magnetization in the kagome layer by looking at putting in different rare earths. And this chiral excitation, which you see this vertical streak there, is always there. So it's seen throughout the series, even in yttrium, which is a helical antiferromagnet. So they all have the same Q dependence and so on. So I'm going to take, I guess I got only 2 minutes left. I have to go through this one quickly, but one more thing I want to describe is the development of scalar spin chirality and the topological Hall effect. So I'll skip this bit about the vector chirality, but in erbium, right, you get this collinear to spiral phase transition. And so you at high temperatures, you have this spiral structure, right? And if I apply a magnetic field in the plane, it evolves into what's called a transverse conical spiral. And so this is where the spiral tilts and the moments cant towards the applied field, which is in this direction. And so in this transverse conical spiral phase, you see this topological Hall effect observed. And so you can look at the magnetic structure. I'll skip that. Here, this is looking down at the transverse conical spiral. You can calculate sort of the scalar spin chirality, or in the continuum model, the emergent field. And it's easy to show that the TCS structure, it has to be 0, because the magnetization is only varying in the Z direction. It's not varying in the other directions. And so so this derivative might not be 0, but this derivative will always be 0. So I shouldn't get scalar spin chirality from the static structure. So that led to a proposal by Igor Mazin and Nirmal Gaimeyer that you can introduce a Magnon field. So you have the static magnetization, and then you have a time-dependent field. If that Magnon field varies in Y, or if you just have a Magnon propagating along Y, then this is also not zero, and you'll get an emergent field. But this field must survive time and space averaging. Otherwise, you won't get a topological Hall. So this is a long story short, but we look at various types of Magnon fields, and this was the one proposed by Mazin, where the Magnon field processes in a plane perpendicular to Z. You can get an analytical expression for it, you can calculate it numerically, and it's time independent, which is interesting. And it's two-dimensional, so it'll vary along the Z direction, but the problem is that ain't a Magnon, right? So Magnons only process in a plane perpendicular to the magnetization. And so if I do that, and I look at a circular Magnon where mu is perpendicular to m naught, I get this Magnon, well, by the way, the arrows are the Magnon field and the solid colors are the emergent field. It's exactly zero, exactly zero. And I can think of other modes, low energy modes like phasons, which will turn the phase of the spiral or the cone, and you can show that that has a time dependence, which will give me a zero on average. So according to us, it's not possible, but we do have these nice models of the Magnons, and so we can do discrete calculations. And so this just shows here that we have a model which represents the field dependence of the excitations, showing these phazon modes and then these polarized ferromagnetic modes. Our phase diagram model agrees with calculations. And so then we can evaluate the scalar spin chirality in a discrete lattice model. So we take the spins, which are the static spins, and for every Magnon mode, we introduce a field which comes from the Magnon eigenvectors. And then you can calculate the spin chirality and the emergent field by taking into account sort of the sense of rotation around every triangle in the system. So we know the dispersions, eigenvectors, so on. You can calculate the emergent field, which is inhomogeneous, but it always averages to zero. So coherent Magnons, I would claim, cannot generate an average emergent chiral field. So this topological Hall effect and why it appears is still a mystery. So I think I'll stop there since I'm already quite over. And I'll leave the summary up there because I'll just take questions. But thank you.
Questions?
Thanks, Rob, for this really nice talk. So in the first part where we discussed the terbium, you told that this is an Ising model, but I was curious, do you have a global axis or it's like a local axis like in the spin ice? Because I mean, I would expect this to be like every side to at least to have different local axes. Because when you're applying this field along the X, it should not be the same, let's say, transverse field for everyone. So how does that actually work? I mean, this local field.
It's a ferromagnet, so.
But I mean, when you have this Ising axis, the same for all sides, or it's really global?
Yep.
Like, oh,
Yeah.
okay, thanks.
Yep.
As I get to the other side, I'll ask you, you may, or comment and ask a question about this other energy scale. You mentioned having loop currents in the vanadium as one possibility. The problem there is that if you have the triple Q vanadium order, you necessarily need to induce a CDW, which you don't see. So I'm not sure that would actually work. Well, but if it's not triple Q, then they would also see that in X-rays, another hexagonal symmetry. So it's kind of but then it's not.
But I think that the orbital magnetization, at least like as seen by STM, is not necessarily a loop current. It's just a strong spin-Berry curvature, which is made non-zero by applying a field.
The question is, and maybe Ian has something he thought about the same, but I know the energy scale is large, but could it be nuclear spins?
We thought about that, yeah.
It doesn't work?
No, because so terbium has a 3/2 nuclear spin, so you get a quartet of excitations. And actually, if you had such a setup, it has to follow Boltzmann factor. So when you have excitations between the nuclear and electronic spin coupled states at very low temperatures, most of the excitations should vanish when you occupy the ground state. And so not only that, but we know how big the hyperfine coupling, and it's not big enough. Yeah, but we did think about that. Yeah.
Two questions. Can you comment here? Can you comment on this scandium time reversal symmetry breaking? Not your data, I believe, but nevertheless. And do you see anything in Bragg scattering on the terbium? Just Bragg peaks at, say, doubling the unit cell type of vectors?
So to answer the first question, I think the only evidence in the scandium vanadium 6 tin 6 for some time reversal symmetry breaking come from USR. So Zurab at PSI had some data which showed that you could have some, you could argue that time reversal symmetry breaking was concomitant with the charge density wave order. But I don't know of any other measurements that came up with a similar conclusion.
Do you see Bragg peaks in the terbium? That would be an antiferromagnet. I mean, even on the terbium side, you should see a modulation, right? Given your variation of the...
So you mean magnetic Bragg peaks?
Yeah.
From vanadium order?
No, from terbium. I mean, it sees that, right?
Of course, yeah.
Yeah.
Yeah, you can map the ferromagnetic order parameter.
No, not the ferromagnetic, an antiferromagnetic one, to see your two different splittings.
Well, I think the ground state would have the same moment, so I don't think you'd get a variation of the size of the terbium moment in that case.
I see.
I mean, you might if by some mixing mechanism, right, you might reduce it, but I don't think that if you had like a vanadium staggered magnetization, I don't think the terbium moment would change.
Ian.
You should have given it to me first, Raphael, and then you could walk up there. So
It's end of...
So for the that's harsh. For the terbium, for the first one, so there are no matrix elements for JX or JY in that doublet. So the other components of the pseudospin are quadrupoles, because it'll have some small amount of MJ of 2 and 4, 2 and minus 4,
Yeah.
and so on. So first, the transverse field will be strain, not magnetic field. But it made me wonder for your two excitations. So just like you said, I could have a what would amount to a quadrupole order if it weren't perfectly hexagonal. It's got a very small quadrupole moment because I've only got small amounts of the 2 and the minus 4 in the 6.
Yeah.
And so it could be a very small distortion. But then the two excitations, one could be a quadrupole flip and the other could be the dipole flip. So what's not allowing that to be the...
well, let me take, let's see, where was
You see what
that?
I mean?
Right, so, initially you said, why are you plotting it versus B66, right?
I thought that was a typo.
and so what you see, but the ground state doublet is plus minus 6 only in the limit where B66 is 0.
Mm-hmm.
So B66 will mix 6 with 0. It will mix states that are separated by M of 6. So if I have a large B66, I will add mix into the ground state 0, which would open up a dipole channel for M equals 0, delta M equals 0. So these gamma 1 and gamma 2, which are the states I would get with this not being 0, there is a dipole matrix element between those.
Even for JX and JY?
Well, it would be JZ. It would be a longitudinal excitation. Yeah,
exactly. So
yeah.
So there is a quadrupole moment in that doublet.
I don't think it matters. I only have 2 states, right?
Mm-hmm.
So I can split those states with some other term in the Hamiltonian, but I can't create an additional state that's quadrupolar out of that.
No, I'm saying that they're embedded in that thing. The pseudospin that describes that doublet has one component is the dipole in the C direction, but in plane it has a quadrupole moment, if you like. the two other components of the pseudosphere. It's the same. Lithium holmium fluoride is the same, actually. The transverse field isn't hx, it's h
Yeah.
squared.
But
So he's saying that tau z,
Yeah,
you're talking about tau z, he's talking about tau x and tau y,
yeah.
or
yeah.
tau x.
I mean, I know the states exactly. I can just calculate the neutron scattering matrix elements. I don't know how I would get an extra excitation from that.
Well, if you couple to a string, then you're going to actually open that gap, right? Because that couples to tau x and then comes off diagonal, so you mix with, anyway.
I mean, we should talk about
We
it.
can
I mean,
talk-
I'm open to any explanation if you think that that could explain it. I think, you have an issue with having two excitations there, so you need at least three states, right? These are zero field, right?
Well, let's solve it.
Yeah, we can talk some more about it.
Any other questions? Okay, so let's thank Rob one more time.